Hi, Roberto. How are you? I saw you opened the room already. Thank you. Can you hear me okay? To unmute, it's all the way.
Okay. I found. Can
Oh,
you hear?
perfect. Yes.
Oh,
Um,
perfect. Yeah,
if you
sorry.
could,
I opened the room, but I realized then that maybe I did something that I shouldn't. So.
it's fine. Um, if you could make me moderator,
Oh
you know,
yeah.
so
Okay.
I can.
Make moderator. Yeah, perfect. Sorry. This
Oh,
is the first time.
perfect. You already know
Okay.
how it works. Perfect. Okay, let me add topics.
Yeah.
I'm adding. Sorry. I'm adding physics and okay. Good. And now I will add your presentation link
Mhm.
and then you can see if this works. How are you today? Everything
No,
good?
yeah. It's very good. Now it's also good weather, so there is the sun after many days of storms.
Oh, good. I'm glad. Did you have floods at all or everything?
No. It's yeah. I now in the office, so it's comfortable to make the presentation without disturbing.
Okay. Yeah, in Portugal we had some floods, but due
Ah,
to
yeah,
too much rain, but I think right now it's also better. So,
yeah. Of course.
how was um everything good? No, cool.
Yeah.
Right now you never know how holidays will be. So, okay, I think the link should work. I added the paper to the chat. I don't know if you know where the chat is. All the way on the bottom left hand, there should be like a
Oh,
speech.
I have a window on in the middle of the screen where
Oh,
it's
you're on the
a room
desktop app,
chat.
right?
So let me try. Okay, yeah, I put a
Okay.
comment, a stupid comment, but it works.
Okay. Good. But I will monitor it for you.
Okay.
So you
Thank you.
don't, it will be fine. And then I'll start by introducing you shortly, and
Mm-hmm.
um, and then we'll do a short interview. I think it's more interesting than having like a traditional like. Of course, I'll say where you went to university and where
Oh
you
yeah.
work now, but then
Mm-hmm.
usually we do like a short interview to kind of um, go over like how did you become a scientist type of question, if that's
Perfect.
okay with you. I think
Yeah, of course.
it's more interactive and more interesting.
Mm-hmm.
And then yeah, so I'll ask like a couple of questions, and then yeah, and then it's time for your presentation and
Okay.
Q&A. So
Of course.
I'm posting on Twitter right now that we're about to start, and yeah, I hope you'll enjoy it.
Yeah.
That's the mm, that's the main part. That it should be also fun for you, not just for us.
It's interesting that in the labels that there are uh, above the window of the chat, there is a magnet alongside physics. So it's exactly what I would talk about today. Magnetism in physics, astrophysics.
Yeah, that one is pretty good.
Yeah.
The engineering symbol is so weird. It's a pizza slice. I don't know who
Oh,
came up with that. I
the
don't know. It's
engineers.
so.
Yes, they can taste good pizzas.
Maybe they order a lot of pizzas when they work.
I don't.
I
I'm teaching at engineering courses, so but they never offered me pizza or something
they
like.
didn't. Okay. That's why. Yeah, I don't know how they came up with it. I always ask myself who came up with the pizza slice. But well, it works so people can find it. Maybe people remember it well.
Mhm, yeah, of course, it's
Maybe.
more catching.
Yeah, probably. Yeah. So, have you? I don't know. Have you ever done any like these podcast type of style things? There's also Twitter Spaces and on LinkedIn now. Have you ever done anything like that?
No, it's the first time that I'm making something like a podcast, let's say. So I heard some of your podcasts in the past before.
Oh, you did? Oh, I
Yeah, yeah,
didn't
yeah. It
realize.
was very interesting to follow, and maybe probably also in the future I will use this
Oh,
opportunity.
nice. Yeah, that's nice. I'm glad you enjoyed it.
Of course.
It's always
No,
nice to hear.
because I didn't know about this particular, let's say, application software, because here in Italy is not very diffused. But now that I know it, it's very interesting to hear some contributions.
Yeah, nice. Yeah, there's this big discussion if Clubhouse will stay independent or because
Mhm.
other social media apps are trying to copy
Oh.
this type of app. Like this started during COVID and then Facebook tried it for a while, but Twitter is doing Twitter Spaces a lot, and some people think Twitter will win, basically.
Mhm,
I
mhm.
don't know, we will see, but it doesn't really matter in the end on what app exactly we do this. As I really like the format and that people get
Yeah, yeah,
to.
yeah. It's very good. It's also easy to reach for people.
Yeah, exactly. And you don't have to. Um, Yeah, do the traditional having like
Mhm.
email invitations and so on.
Oh yeah, yeah, yeah.
Just join. Yeah.
No, I'm only, but it is not my problem because all the results that I will show from the science paper today are already published, so there are no problem of embargoes. But I will also show some previews, some results that are not published, but the journal at which we sent the publication has no problem in diffuse before the publication date. So
Oh,
you
that's
will
good.
enjoy the first data of the new magnetar that I think nobody see up to now.
Oh, wow, that's so exciting.
It's a really preview. No,
Oh,
better.
wow.
There are also other presentations, for example, in seminars in some universities, but I think that this is the first public one.
Oh, wow. That's really exciting. Thank you
Yeah,
for
yeah, yeah.
doing that. Um, that's an honor.
No, yeah. I hope that you will enjoy because the topic is very specific in some cases, so maybe people cannot be very, let's say, interested in also enter more in depth about these details. So I will try with a presentation, let's say, more simple, also for a public, a general audience. But I will really hope that you can appreciate the discoveries that we did.
Oh, yes, for sure. I think it's so fascinating, especially because it's very far away from the research I usually do
Mhm.
and learn to do. So I'm always very curious. And
Which is the spirit of science, after all.
that's true. There was a guest speaker. He said, we asked the question,
Mhm.
how did you discover like your curiosity for science? And he said, that his family, I don't know who exactly
No,
was used.
it's a curious story indeed, because it started when I was a child, of course, like I think all people that work in this field. But I also asked myself why I am so interested in this kind of science, so in astrophysics. But I think it's written in my DNA, because also my father, which was a bank layer up to some years ago, and he was really passionate about these kind of topics. So I started when I was a child, and also with a small telescope. And then also, I think I have to thank my teacher at the middle school of maths, that introduced myself to science in general. And then I continued during my life uh, to study this kind of topics. And at the end of the university, I decided before to take a grade in physics, and then to enter more in depth into astrophysics. So it was very interesting from this point of view. And it was natural for me to follow the way of the neutron stars, because I don't know if you never listen to in YouTube. There are some videos about the pulsar sounds. So the sounds that are in a sense recorded from pulsars, for far pulsars that are being observed in the radio band. And when I listen to this video, I am really fascinated about the sound of the universe. That sound, it's a kind of music, let's say, that the universe is transmitting to us. So this is my passion about this kind of science.
That's beautiful, and it's interesting because we met the newsroom here, and then there was released the sound of
Pulsars.
black, no, also black hole.
Oh yeah, yeah,
And
yeah. The sound of the black hole now, it was really, really impressive to listen.
yes, and it was so dark, like it was
Yeah.
like a
Of
horror
course they
movie.
are rendering. Of course they are rendering, but like I think that in the chat is also they are sonified. Yes, is correct. But for pulsars is different, because the pulsars emit in radio bands. So in a sense, it's like listening to the radio, the communications of these kind of objects. For black holes, it's different. Is a rendering so, of the sound, but it's still very impressive, because there is a science base in this kind of sounds. So yes, it's impressive to listen.
Yeah, so do you like music in general? Like, do you also
Ah,
have a
yeah, yeah,
passion
yeah.
for
I
music?
also studied music in my life, piano in particular. I was graded in the conservatory here in Italy, and also in this case, it's interesting to see that music, after all, is science. For example, for piano, is the length of the string in the piano, in the strings instruments, are let's say related to the notes by precise mathematical relations. So it's a kind of science, but here the sensitivity of human beings enter in a sort of dialogue with science, and create really masterworks. So it's really fascinating also in this case.
Yeah, that is fascinating because we had quite a high percentage of speakers that had both, like relatively almost professional music career and science. So it's really interesting how that also seems to be correlating this.
Oh yeah, oh yeah.
Um, yeah, and our guest speaker from yesterday, who is at the Brookhaven lab at the Particle Collider, he's also here. Welcome, Zhangwu. And Frank is here. He was very looking forward to your
Mhm.
talk. So
Oh,
Yeah, I wanted to introduce you
I am
both.
honored of this.
Yes, of course. And let me give a short introduction. We almost went through the interview already about how you discovered your passion for science. So, welcome everyone to Science Society, and of course, a special welcome to Dr. Roberto Taverna. And he did his education at the University of Padua in Italy, and he did his PhD there in 2016 in the Department of Physics and Astronomy. And then he did his he is a researcher at the University of Padua in Italy, and he did his he also went to the University of Rome as a research fellow in the Department of Metaphysics. And you can check out, I'm just adding the link in the chat, the website, the organization website here. And it's such an honor having you here. And yeah, as I said, we already talked about how you developed interest as a child in science and physics, which is it's really wonderful to hear that you had support also from your teacher in middle school. I think that's really important too, to learn that. And the next question would be, is there maybe an interesting background story about this specific project, how it came about, and how you had the opportunity to work on this project? Thank you.
Oh yeah, I think that there is a curious story about it because when I started, of course, I asked for a thesis on neutron stars to my professor when I take the grade in physics, the master thesis, and my professor proposed this problem of polarimetry, so polarization measurements in neutron stars. It was a very pioneering field of research at that time because no instruments were launched. There was one, but it was then not accepted by NASA, if I remember well. And so when I talked of this argument also of this topic around the world, people also asked to me, but do you really believe that it will be possible to measure polarization in neutron stars? And I was always, I trusted to these methodologies that we were studying. And in the end, last year, in December 2021, so 2 years ago, but almost 1 year of operation, it was launched this new satellite. And indeed, it has been a really nice discovery that also our research, and my research in particular, was confirmed in a sense, as I will show in this presentation.
Well, I'm so glad that worked out. So that's wonderful. Congratulations for that. And yeah, everyone, the slides are pinned on top of the room. Please access them. And Roberto, the stage is yours. Thank you.
Okay, so there are a lot of slides in the presentation, so I will mention every time I change slides, I will try to mention the slide that we will be. So, so you can see the summary at slide 2. I will discuss the recent polarization measurement, as I just said, in the X-rays for two strongly magnetized neutron stars that are called magnetars, and I will also introduce what are magnetars. These polarization measurements have been performed with the XP satellite, which is a mission organized in collaboration between NASA and the Italian Space Agency, launched in December 2021. And just this month, in January, it ended the first year of operation. So it's a very new topic in astrophysics. So I will briefly introduce neutron stars and magnetars in general. Then I will describe what is polarization and what are the polarimetric techniques in X-ray astronomy. And finally, I will discuss two measurements. One is that we discussed in the science paper, which is also linked in the chat, for a magnetar which is called 4U0142 plus 61. And the other one, it's a sort of preview because the paper is in the final revision stage, so it will be accepted hopefully in some days. But this is, I think, is the first time that I present these results in a public meeting. So I hope you will enjoy it. Okay, so now I am at slide 3. And let me start giving a general introduction on neutron stars. So neutron stars, also for the general audience, are all that remains of massive stars, where with massive, I mean between 8 and 25 times our sun. So at the end of their life, the core of these giant stars collapses under the action of their own weight, and their external layers are expelled in a supernova explosion. And the mass of what it remains, so of the core of the star, is expected to be within 1 or 2 solar masses, but the diameter is quite small, not greater than 20, 30 kilometers. That means that a neutron star can comfortably occupy a region like that of Manhattan Island, as you can see in the artist impression in slide 3. This means that neutron stars are extremely dense objects, and the classical comparison in all the presentations to the general audience is that a teaspoon of the matter of a neutron star would weigh about the same as the Everest Mount on the Earth. So they are very dense. So now I'm at slide 4. Neutron stars have other weird properties, of course. First of all, they are fast rotators, and their spin periods are usually detected using their pulsed emission, as you can see in the animation in slide 4. And the measured spin periods are typically in the range between 0.1 and 10 seconds. Moreover, they are quite precise clocks, in the sense that the spin period vary quite slowly in time. This can be estimated through the spin down rate, which is the time derivative of the spin period in time, and it takes typical values between 10 to the minus 20 and 10 to the minus 10 seconds per second. So the neutron star rotation has to slow down in time, even if very slowly. And it is indeed the slowing of the rotational motion of the neutron star that is responsible for another important property, which is that neutron stars are endowed with ultra-strong magnetic fields. In particular, making the calculations, assuming, for example, the conservation of the magnetic flux in the collapse of the core, it can be shown that the surface magnetic field intensity of these objects assumes a typical value of the order of 10 to 12 Gauss. That means 10 to the 8 Tesla, according to the values of the spin down rate and also of the spin period. And to give you an idea of the order of magnitude of this magnetic field, I put some examples in slide 5. So, for example, the magnetic field on the surface of our planet is around 0.5 Gauss. And 1 Gauss is the typical magnetic field of the magnets that we have at home. Stars, like our sun, especially during the solar storms, can arrive to higher values like, for example, 1000 Gauss. While the strongest magnetic field we have achieved in laboratory is of the order of 10 to the 4 Gauss. So the typical magnetic field of a neutron star, which is 10 to 12 Gauss, is 100 million times stronger than the strongest magnetic field we can achieve on Earth. So very huge magnetic field, to give you an idea of the order of magnitude. Given the importance of the spin period and of the spin down rate, now I am at slide 6, spin period and spin down rates are used to classify, in a sense, neutron stars in the so-called PP dot diagram, which is shown in slide 6. In this diagram, we can identify different populations of neutron stars. For example, if you look at the center, there is a most populated cloud of dots, which is the population of rotation power pulsars, which are also called radio pulsars because they were originally discovered observing their pulsating emission basically in the radio band, as I said. Instead, looking at the bottom left corner of the diagram, there is a smaller and more diffuse population, and these are the so-called millisecond pulsars, because their spin periods are of the order of the millisecond. And these particular neutron stars are characterized by accretion phenomena, so they accrete material, for example, for a companion star in the vicinity. And this can accelerate the rotational motion at the expenses of the magnetic field, which is typically smaller than that of normal pulsars, 10 to the 12 Gauss that I mentioned before. Looking instead at the top right corner of this diagram, you can see the population of the so-called isolated neutron stars. They exhibit some strange properties compared with normal pulsars. For example, they emit predominantly X-ray radiation. They are normally characterized by stronger magnetic fields with respect to normal pulsars, so even stronger. And some of them have also been observed to emit violent explosions of X-rays or also gamma ray radiation. And to complicate things, as the name suggests, they are isolated neutron stars. So we cannot explain this particular behavior in terms of accretion, as for millisecond pulsar, of material from a companion star. And some of these isolated neutron stars are believed to be endowed with a magnetic field also 100 or 1,000 times stronger than for common pulsar. And for these reasons, they are called magnetars, which is the topic of our published work. So now I am at slide 7. And let's enter more in depth in the class of magnetars. I put a short historical summary in this slide 7. Actually, magnetars were not immediately identified as neutron stars. The first magnetar to be observed in 1979 was dubbed soft gamma repeater because it came forward as a huge blast of gamma ray radiation, which overloaded the satellites in orbit around Earth at that time. So the first association was not with the class of neutron stars, but with the class of gamma ray bursts, which are very strong explosions associated to particularly powerful supernova events, or also more recently to the merging of two neutron stars. However, there were few problems with this association because, first of all, gamma ray bursts are one-shot phenomena. So they can happen only one time, of course, because they are related to the death of a star or to the merge of two objects. So they can occur only one time, while the soft gamma repeaters were observed to be repeated more than once from the same location. For this reason, the name of repeaters. And usual gamma ray bursts were also observed to arrive from distant galaxies, while soft gamma repeaters, like the first magnetar observed, were observed only inside the Milky Way or at most from the Magellanic Clouds, which are close to the Milky Way. And another class of objects subsequently identified with magnetars was initially called anomalous X-ray pulsars. So in this case, it was understood that they were neutron stars, but they show apparently the properties of common pulsars, but they emit in the X-rays, first of all. Moreover, also these sources were observed to emit powerful explosions of X-rays, and their luminosity in general appear to exceed the energy losses due to the rotation. So these objects cannot be powered by rotation, or at least not entirely powered by rotation as for normal pulsars. And for this reason, the name of anomalous pulsars. So now I'm at slide 8. Only in 1992, it was successfully proposed a theoretical model, later known as the magnetar model, according to which both soft gamma repeaters and anomalous X-ray pulsars were neutron stars, powered by their particularly strong magnetic fields. And this is the reason of the name of magnetars, to distinguish them from pulsars, that means pulsating stars, while magnetars means magnetic stars. According to this model, the internal magnetic field of magnetars is much stronger than for normal pulsars, and also highly wound up, so with a strong transversal component, as you can see in the sketch on the left in slide 8. And this transversal component can also develop a strong magnetic stress on the crust of the star. And this stress is able to overcome the rigidity of the crust itself, deforming the surface of the neutron star. And this phenomenon is called starquake. So a large amount of energy is released, and this could give origin to the giant explosions observed from these sources. Moreover, following the deformation of the crust, the external magnetic field lines, as you can see in the animation at the bottom right of slide 8, so the magnetic field lines can deviate from the usual dipolar shape. The dipolar field is the typical field of our house magnets. And it becomes a twisted field, a twisted magnetic field. Now, if you change at slide 9, at variance with the dipolar field, a twisted field requires that currents flow along the closed field lines. So charged particles must come out from the star. This is represented in the sketch at slide 9. The presence of these charged particles creates a sort of magnetosphere, so a region filled of charged particles around the neutron star, in which the photons that are emitted from the star surface can be scattered. And this phenomenon is called resonant Compton scattering or resonant cyclotron scattering. Now at slide 10, the Magnetar model found a first confirmation from the spectral observation, which means studying the flux of the collected photon as a function of their energy. In the soft X-ray band, magnetar spectra appear to be characterized by two components that are superimposed. A thermal component, the blue one in slide 10, which is a black body component, and a non-thermal component at higher energies, which is a power low tail. The thermal component is due to the photons emitted by the cooling star surface and arriving to us practically undisturbed. In other words, we can imagine that the star surface is a sort of hot iron ball, which is cooling. On the other hand, the power low tail can be due to these photons that are scattered in the magnetosphere that I mentioned before. There are also other sources that don't show the power low tail, so they show rather a purely thermal spectrum. That means that in this case, for example, scatterings are not much effective, or for example, the twist of the field lines is not strong at the moment of the observation. So now I am at slide 11. After this introduction, let's say theoretical, about neutron stars and magnetars, let's come to the very topic of the presentation, which is the measurement of polarization in the magnetar X-ray emission. First of all, let me only clarify what I mean with polarization of electromagnetic waves. So according to the semi-classical view of electromagnetic propagation that we used in our paper, each photon is associated to an electromagnetic wave, which is in turn determined by an electric field and a magnetic field oscillating perpendicularly to the propagation direction Z in this picture at slide 11. And the magnetic field and the electric field are also perpendicular to each other, as you can see in the picture. So each photon is associated to the propagation direction of the wave, the wavelength, or equivalently the photon energy, and the oscillation direction of the electric field, which is called the polarization direction, is the red one in slide 11. It is sufficient to determine the oscillation direction of the electric field and not also of the magnetic field, because that of the magnetic field simply follows, being orthogonal by definition to that of the electric field. I will only consider plane waves. So now I am at slide 12. In the general case, if one takes a collection of many photons, their electric fields will oscillate in any possible direction, and the total radiation collected at infinity do not have a precise direction. In this case, in the left of slide 12, the radiation is called unpolarized. However, there can be some physical processes which force the electric field of photons to oscillate preferentially along one precise direction, as on the right of slide 12. In this case, radiation is said to be linearly polarized. For all the other intermediate cases, we can define a degree of polarization, which gives the fraction of photons which are polarized in a certain direction. So with the electric field oscillating in a certain direction. And of course, the unpolarized case corresponds to a polarization degree PD equal to 0 on the left, while the linearly polarized case on the right to a polarization degree of 100%, only to explain what I mean. So now at slide 13, we can ask ourselves, we have defined the polarization, but what we have to expect for the polarization of magnetar emission? Is it polarized or unpolarized? Well, strong magnetic fields like those around magnetars, which are very strong, can influence the direction of the polarization of the emitted photons. In particular, as shown in this picture in slide 13, it can be shown that when the magnetic field is strong enough, photons are forced to be polarized only in two directions, which are roughly speaking parallel and perpendicular to the magnetic field of the star. They are called ordinary mode, the parallel mode, and the extraordinary mode, the perpendicular mode. So this means that these ordinary and extraordinary polarization directions are orthogonal to each other. So the two orientations of the electric field differ by 90 degrees. And remember these 90 degrees, which will be very important in our discovery. And this property is a property of the vacuum in the presence of strong magnetic fields, and it is called the vacuum birefringence, because in strongly magnetic fields, the vacuum behaves exactly like a birefringent medium. And so the answer to our question of before, magnetars are polarized? Yes. The radiation should be strongly polarized in these two modes, parallel or perpendicular to the star magnetic field. So now I'm at slide 14. We have to take into account that, we have to say that the radiation from magnetars is polarized, but can we observe the polarization from magnetars? The problem is that the magnetic field around the magnetar is not uniform, has not a single direction. If you take a look to the cartoon in slide 14, the magnetic field close to the star surface follows curved field lines, and it is tangent to these curves. For example, the field lines of a dipolar field as a first approximation. So the direction of the magnetic field changes in general point to point on the star surface. Now, if we assume for simplicity that the electric field of the photons makes the same angle with respect to the magnetic field at a different point, when we sum together all the photons emitted from the star, the net result is that of unpolarized radiation, like before. You can see in the square on slide 14, due to the fact that the star magnetic field direction varies point to point. So according to this conclusion, there should be no hope to observe a degree of polarization different from zero for radiation coming from a neutron star. But there is an effect, I am slide 15, there is an effect predicted by the quantum electrodynamics, which is the quantum theory of electromagnetism, that comes to our help. It happens that strong magnetic fields are indeed able to influence the vacuum in a sense, to polarize the vacuum. This is due to the fact that the quantum vacuum is not really empty, but there are virtual electron-positron pairs. And these electron-positron pairs flip in and out of existence in a very short time, of the order of 10 to the minus 44 seconds, which is the Planck time. So due to this very short time, they usually do not influence the surrounding world. We can't feel them. But if the magnetic field is very strong, these electron-positron pairs are stretched, let's say, along the direction of the magnetic field of the star, and this modifies the properties of propagation of the photons. And this effect is called vacuum polarization. It is curious because vacuum polarization was theorized in 1934 by Heisenberg and Euler, but it has never been tested as yet in laboratories. And the reason is simple to understand, because we cannot achieve the necessary magnetic field in our Earth laboratories. As I showed at the beginning, there is a huge difference between the magnetic field we can achieve in laboratory and the magnetic field of neutron stars. Nevertheless, it can be shown that these stretched virtual pairs that are represented in slide 15 have a visible effect on the polarization of the photons that propagate in the vacuum. I don't want to enter into much detail on this because it's a very specific topic, but let me only say that the net effect of vacuum polarization is that we can indeed measure a remarkable amount of polarization. from magnetars, despite the fact that the star magnetic field changed direction point to point. So in a certain sense, measuring a non-negligible polarization for the radiation coming from a neutron star could be an indirect proof of the effect predicted by Heisenberg and Euler in 1934. Okay, so now I am at slide 16. We have seen that magnetar radiation is likely polarized and that we can also measure this polarization from Earth. There is hope to measure this polarization. Now let's have a look on what is the polarization. So in what direction is polarized the radiation that we collect from magnetars, and at what degree of polarization? It is 100%, it is 60%, or 0. Of course, the polarization properties of the emitted radiation, as you can imagine, are strongly related to the emission process from the surface. So on the physical state of the neutron star surface. And so the question is, what kind of material we have on the surface of a neutron star? Is it a solid surface where we can place our feet like on the Earth? Or is it something different, like, for example, I don't know, the atmosphere of a star, of a normal star? So let's give a look on slide 16, where I put two simple sketches. According to the very first neutron star models that are dated back to the 70s, the surface of neutron stars was believed to be a solid surface, essentially composed by EV elements like iron that originate from the latest stellar evolution stages. Of course, neutron rich, so with a high number of neutrons inside, because they are neutron stars. However, more recent observations of isolated neutron stars show some broad absorption lines in the spectrum, and these absorption lines are suggestive of the presence of an atmospheric layer that covers the surface. Because if we saw absorption in the light, we can think that the photons at a certain energy have been absorbed by the atoms of a gas layer close to the surface. Of course, this atmosphere on a neutron star should be much different than around the Earth, for example, or from standard stellar atmosphere like our Sun. For example, since neutron stars are very dense, as I mentioned before, the surface gravity, you can imagine, is very strong. It's billions times that on the Earth. And so the atmosphere around the neutron star should be only a few centimeters thick. But despite this thickness, we can see, in any case, the effects on the spectra of the radiation. However, we have to take also into account that in the presence of very strong magnetic fields, matter, and so also the gas of the atmosphere, behaves very differently with respect to normal conditions. In particular, it can happen that the gaseous atmosphere condenses. So you can imagine to a rain on the star surface, even if the temperature of the star surface is of millions of degrees, but it can condense in the presence of strong magnetic fields. And in this case, the atmosphere settles on the surface, leaving exposed the solid surface like before. So there are two possibilities. The radiation can arrive directly from the solid surface, or it can be reprocessed in an atmosphere which covers the star surface. Now, let's change at slide 17. Theoretical models show that having an atmosphere or having the solid surface exposed does not make much difference studying the spectrum, so the flux of photons as a function of the energy. For this reason, even if the astrophysical community performed many spectral measurements of neutron stars and magnetars up to now, we couldn't say much about the physical state of the surface because the spectra are very similar. You see, it's impossible to distinguish if we have the feature of an atmosphere or of the condensed surface. But if you go to slide 18, you can see that the predicted polarization in the two cases of atmosphere or solid surface is very different. If an atmospheric if an atmospheric layer is present on the surface of the neutron star, we can expect a high polarization degree. You see in the plot on the left, it is greater than 80% for the total photon collected. Well, if the solid surface is left bare on the surface, the polarization degree is not larger than 15-20%, as you can see in the plot on the right. Moreover, this is not shown in the plots, but it's an important property. In the case of the atmosphere, the photons are predominantly polarized in the extraordinary mode, which means perpendicularly to the star magnetic field. While in the case of the solid surface, we can have both ordinary and extraordinary modes, so both photons polarize parallel or perpendicular to the magnetic field of the star. Moreover, if you change to slide 19, we must not forget that before to arriving to us, the photons may undergo scatterings, as I mentioned at the beginning, in the magnetosphere of the star, which is not the atmosphere, is something different. It is farther from the surface. As I mentioned before, this can produce a power law tail in the spectrum that I also show you in a previous slide. And theoretical calculations show that the net effect of these scatterings in the polarization is to set the polarization degree to 33%, around 33%, perpendicularly to the magnetic field, so in the extraordinary mode. And you can see an example in slide 20 of what happens if scatterings are taken into account. Here, it is shown the difference between the cases with and without the scattering for both the atmosphere case on the left, top left, and the solid surface case on the bottom right. So in any case, when we take into account scatterings, the polarization at high energies, where there is the power law tail in the spectrum, saturates at a value around 33% in the extraordinary mode. So let's change slide 21. We have now defined all the theoretical framework we need. And so let me only say something about how we measure this polarization for magnetars. As I mentioned at the beginning, we use the satellite XP, which is a collaboration between NASA and the Italian Space Agency. And XP is essentially an X-ray telescope, but it can also measure the polarization of the X-ray photons using the gas pixel detector technology. The sketch here reported is a sketch of a gas pixel detector. And how it works. There is the photon that enters in the detector. The detector is a cell filled of a particular gas mixture. And there is an effect, a physical effect, which is called the photoelectric effect, according to which the photon can be absorbed by an atom of the gas with the expulsion of an electron. And according to the theory, the direction of the expelled electron is the same as the polarization direction of the incoming photon. So in this way, XP can reconstruct the polarization of the radiation. I remark that these are the first polarization measurements in the X-rays since more than 40 years. Because the only other satellite with onboard an X-ray polarimeter was launched in 1978, but it relied on a different technology, very pioneering technology, and it could observe only two sources and no magnetars. So these are the first ever measurements of polarization in the X-rays for magnetars. Now, if you go to slide 22, I show the position in the sky of the two magnetars we observed with XP. On the left, we have the magnetar 4U0142 plus 61, that of the paper on Science. It was observed in February 2022, and it is located in the Cassiopeia constellation at a distance from the Earth of around 13,000 light years. The second one is instead the preview that I mentioned before. So it is the magnetar 1RXS J1708 minus 4008, etc. This is the long name. It was observed between September and October 2022. It is located in the Scorpio constellation. And you see, we don't know exactly what is the distance of this source, but roughly speaking, we can say between 16,000 and 32,000 light years from the Earth. And the two sources were observed for around 1 million of seconds both, so around 20 days for both. And this allowed us to reach a good statistic to perform all the possible analysis, so both the spectral analysis, like previous instruments, and also the polarization analysis, of course. So now in slide 23, you can see for what concerns the timing analysis, which means the photon flux as a function of the time, we reconstructed the so-called pulse profile. So where is the pulse of the neutron star in time? And this allowed us to measure the spin period of the star, as well as the spin down rate, we also found values that are compatible with the previous investigations in the literature. And also the magnetic field is what we expect, around 10 to the 14 Gauss for both the two sources. In slide 24, you can see instead the result of the spectral analysis, so the photon flux as a function of the energy. Also, in this case, we found the value and properties which were also already investigated, in particular for the first magnetar on the left, 0142. We found that the spectrum can be decomposed as a black body plus a power law, if you remember at the beginning. And the power law in particular suggests that photons are undergoing scatterings in this source. Instead, for 1708, you see many lines. Why? Because there is no power law in this source. We have only thermal components, so we can say that there is no scattering. The external field lines are not twisted so much. But the problem is that in previous investigations, there was a power law tail. So we should check if the instrument was broken in this case, and we compare the observation by XP with the observation of other instruments which are swift and nicer, performed within 1 month with respect to the XP observation. And also these other instruments found no power law tail. So the conclusion is, yes, the source is in a different state, let's say, with respect to the past. Okay, let's come to the clue, the polarization measurement, which is shown in the slide 25. There is a polar plot. You can see both the polarization degree and the polarization direction in this plot. In particular, the polarization degree is on the radial coordinates, so the amount of polarized photons is higher going outwards with respect to the center, while the azimuth indicates the polarization direction in the plane of the sky. 0 degrees here correspond to the direction of the galactic north for reference. The measurements in the diagram are represented by the small crosses, if you can see them, which are within the corresponding error contours. And this plot in particular refers to the first magnetar, 0142. As you can see, the polarization direction varies from around 50 degrees east of north at smaller energies to 40 degrees west of north at high energies. If you see, there is a net difference between the two orientations by exactly 90 degrees, and this was really surprising. We expect this, but of course it is surprising that the theory works. And at the same time, if you look at the polarization degree, it is quite small at low energies. It is on the left of the polar plot. You see there is 15-20% at low energies, and then up to 35, let's say, percent at high energies on the right. So why this behavior is so interesting? First of all, because as I mentioned, the polarization direction changes by exactly 90 degrees. And as I mentioned before, if strong magnetic fields are present, radiation is expected to be polarized only in two orthogonal directions, parallel and perpendicular to the star magnetic field. Hence, this swing of the polarization direction is strongly suggestive that there is a strong magnetic field around this source. This is very important because the value of the magnetic field that I mentioned with the spin period and spin down rate, 10 to the 14, and so on and so forth, is only suggestive of an order of magnitude of the magnetic field. It is not a real measurement. So nobody has never shown beyond any reasonable doubt that magnetars possess a strong magnetic field up to now. But the fact that the photons are polarized in these two orthogonal directions points strongly in favor of the strong magnetic field in magnetars. Is a sort of smoking gun. And there is another property. If you look at the polarization at high energies, 35%, is a value which is impressively close to that value, 33% that I mentioned before for scatterings. If you remember, I saw that when there is scattering, the polarization should be 33% in the extraordinary mode. And we verified that there is a value which is within the error compatible with 33%. And also there is another important information hidden in the plot as slide 25. I mentioned now that the polarization direction of the photons at high energies, if scatterings are present, should be let's say, perpendicular to the star magnetic field in the extraordinary mode. So since there is the 90-degree swing, those at low energy should be parallel to the magnetic field in the ordinary mode. Now, if you remember, there is only one model of surface emission which is compatible with polarization parallel to the star magnetic field, which is not the atmosphere, it is the solid surface. So this could be the first time we observe radiation coming directly from the solid surface of a neutron star, so without the presence of an atmosphere. Of course, what I'm telling you now is only qualitative, so a sort of comparison between model prediction and observed data. But we also produce some precise numerical simulations to tell these things. And these simulations are represented by the stars that you see in the plot slide 25. And you can see that indeed we found a good agreement between the theoretical expectations and the data, because the stars follow the data, so they falls inside the contour at the corresponding energy. So concluding in slide 26, you see that the better agreement between our theory and the observation is obtained not for radiation coming from the entire star surface, but from a limited region of the surface, so a belt localized around the magnetic equator of the star. And this means that the part of the solid surface which could be exposed is not necessarily the entire surface, but could be only a region on the surface. Now in slide 27, you can see the polarization measurement for the other magnetar, and this is new. So nobody see this before in public meetings. This is for the magnetar 1708. As you can see, there are some differences with respect to the other magnetar. First, the polarization direction does not change by 90 degrees in this case, but it remains constant at a value which is around 60 degrees west of north. Second big difference, if you see the scale in the radial coordinate, the polarization is much higher than before. It can arrive up to 80% at high energies. And also in this case, we can draw some conclusion. If you remember, we have only one model of surface emission that predicts polarization so high, which is the atmosphere model, if you remember slide 18. The atmosphere model predicts indeed a polarization greater than 80%. Of course, here we have a sort of problem, because in the atmosphere model, polarization is 80% at all energies, while we have found also polarization 20% at small energies, as you can see in the polar plot, slide 27. So this means that there is to be more than the only atmosphere. There is to be also another region with the solid surface exposed. And the possible scenario is shown as slide 28. So there could be still an equatorial belt, like emitting like a solid surface, like in the previous magnetar, but this time with the addition of another region and covered by an atmosphere, which is located, for example, at the pole, at the magnetic pole of the star. Or these two regions could be also some spots on the surface located in different locations. Finally, in slide 29, I showed that also in this case, we performed some precise numerical simulations, and both these models that I showed you before in slide 28 can well explain the data. So the colored curve, the solid curves, and also the dashed curves are the predictions of the model. And the blue cyan dots with error bars are the XP measurements. Okay, so in conclusion, I am at slide 30. We had the opportunity to explore for the first time ever the two magnetar sources in polarized X-rays, and this new technique, together with the other analysis, like the spectral analysis, allowed us to learn some important lessons. First of all, we confirmed that magnetars are endowed with ultra-strong magnetic fields, thanks to the 90-degree swing of the polarization direction in the first magnetar. Then our investigation led further support to the magnetar model. In particular, we could see that the power law tails in the spectra correspond to a polarization of around 33%, exactly the value predicted by the theory. And also, we could provide a first hint of emission coming directly from the solid surface of a neutron star. And moreover, we have seen that likely atmospheric and solid surface can in principle coexist in the same source, as I showed in the last slides. Or we can also think that there are other models to explain this data, but we have no numerical simulations for these other models. So there are models still in development. We can study them and we can maybe perform other investigations. While we are planning also to observe other magnetars with XP in the second year of operation of the satellite, and it could be extremely interesting to see if our theories are still confirmed. So stay tuned about this. And thank you very much for your attention. I am glad to answer to all your questions.
Thank you so much, Roberto, for this wonderful presentation and for explaining the principles you use so well, that gave us like a deeper insight into the study, and also for sharing not published data yet. That's really an honor. So thank you so much. And everyone, if you have questions, please raise your hand. Feel free to also leave questions in the chat, and we will read them out for you. And I know Frank was really curious to for this talk, so I want to give him the opportunity to ask first. Go ahead, Frank.
Yeah, thanks, Katerina. Yeah, thanks, Roberto, for the excellent lecture. It's definitely much beyond my paper to do. I mean, I understand the, but it's definitely so much information here presented, and let me just try to like a homework to get a full picture that what has been explained. You're explaining that there are two. I'm looking at the picture of the slide 26. So the scatter ones produce the X mode, and the non-scatter one, say from the solid surface without the atmosphere, that's the O mode.
Yeah.
Am I?
We think this is our interpretation, of course. We think that since there are these two different modes which are highlighted in the observation, and since high energy photons, if they arrive to 33%, they should be in the extraordinary mode, according to the theory. Now, the low energy photons are consequently in the ordinary mode, and the low energy photons should arrive directly from the surface of the neutron star, because photons at those energies will arrive only from the surface. So the only model for which we have ordinary photons in presence of strong magnetic fields, of course, from the neutron star up to now is that of the solid surface. Of course, there could be other models. For example, in our paper on science, we mention a couple of other models. For example, there could be a particular kind of atmosphere that behaves more like a solid surface. But these are more still speculation at this level. We are waiting for numerical simulation, which are more, let's say, rigorous also to be compared with data.
I see. So just to understand the basic a little bit more, these slides 13, I was a little bit distracted while we were going through the slides. So for the ordinary mode, the polarization is arbitrary. It has it's not the as the other one is confined to only two perpendicular directions. So for the ordinary, it's arbitrary. For the low energy.
Yeah, it's let's say I presented them for simplicity like parallel and perpendicular to the star magnetic field, but this is not completely true. They should be, as you can see in slide 11, the electric field should be in any case perpendicular propagation direction, which in slide 13 is K. So the blue and green arrows should be perpendicular to the black one. And then they can be or in the plane, so parallel to the plane made by the propagation direction and the star magnetic field, or perpendicular to this plane. So also in the ordinary mode, the arrow, let's say, is only in a precise direction. But it is, let's say, forced to be in the plane made by K and B. And in this plane, it should be, by definition, perpendicular to K.
Right, and for the this slides, I mean the cartoon on this slides, I 100% understand. It's just EM wave, right? So it has a propagation, and you can prove that the two fields are perpendicular.
Yeah.
To the propagation. I'm just trying to understand what is the. Can you repeat the you were explaining the what is the difference of the polarization of EO versus EX in the strong and weak energy
Okay, no, the only
scenario?
difference between the two mode of propagation is the direction of the electric field. So if you
Which
imagine that,
is
which is the blue and the green arrows here. So if you put the arrows, let's say, close to each other, you will see a sort of cross. They are 90 degrees one with respect to the other. So one oscillates, let's say, vertically, and the other one horizontally. So it is in perspective in this slide, so you maybe cannot understand very well. But let's imagine to have the plane of polarization of the plane of the screen. The extraordinary mode is a vertical line, so the electric field oscillates vertically, and the wave is arriving towards you. And the ordinary mode is oscillating horizontally. So the difference, the only difference is that the electric field of those waves oscillates in orthogonal directions. So with a difference of 90 degrees, which is what we observed if you look at slide 25.
Is that okay, Frank? Because Dr. Zhangbu, he had a question. If you,
sure. I mean,
yeah.
I'll just wait for if there's more time. Yeah. By the way, just quickly, the is it the so is the line of sight issue here for your observation window?
Sorry, can you repeat the question?
Is the line of sight towards the object, the star, is the issue to give rise to some observational window? Or is that relevant question here?
Oh, let's say, yeah. For the observation in general, we have to have the line of sight, which is, let's see, free from other objects. For example, the most important problem is the sun. But we can observe any direction. Of course, we have to take into account that having the line of sight does not mean that we know all the other geometrical properties of the source. For example, the inclination of the rotation axis and so on and so forth. But this can be constrained also by polarization and of course also on the spectral radiation. So there is no problem with the line of sight for the observation. It's not an issue.
Okay, thank you.
You're welcome.
Yeah, please, please go next.
Okay, can you hear me?
Yeah.
Okay, great. So congratulations. This is really exciting measurements. And so I have two questions related to your earlier discussions about the vacuum birefringency and polarizations. My understanding from your discussion is all the photons emit, although they can go through the magnetic field, but because most of them scatter by the particles, which make the polarization about 33%. So the effect of the vacuum birefringence and polarizations are basically kind of washed out by the scattering. But I mean, the reason I'm very interested in because when 2 years ago we tried to publish a paper on the vacuum birefringence, we searched the literature, and some of the authors published a paper in 2017 that there is evidence of the vacuum birefringence by looking at the polarizations of the lights, which you measure from one of the neutron stars. Can you explain more whether that still holds, or from the new measurement you can actually prove most of them are actually scalar reprocessed?
Okay, the vacuum, thanks for the question because it's very interesting, of course. So for the first part of the question, that of the scattering, actually, also if photons underwent scattering in the magnetosphere, the effect of vacuum birefringence, vacuum polarization is not washed out because it can be shown that the last scattering radius, so the distance from the star at which the scattering can occur, is much smaller than the polarization limiting radius, which is the limit in which vacuum polarization effect can occur. So let's say that we can associate to the star a original polarization imprint, which is that given by the surface emission plus the magnetosphere, so the scattering. And this is preserved up to us because of vacuum polarization. So this is the first, I think, the answer to the first part of the question.
So
Yeah.
just to follow up, so the evidence for vacuum birefringence now it's proved, because before I think the statistical error bar is very big. That's why
it's the part of the work that I would to omit in my presentation now because it's the problem. It's more complicated than what I presented, in the sense that these. So, in principle, if you see a very high polarization degree, like those, like that in the second magnetar, 80%, in principle, is sufficient to say that yes, if vacuum birefringence was not present, you couldn't observe such a high polarization degree. But the problem is that this treatment holds only if we consider radiation coming from an extended region of the neutron star, because what we observed is not the real direct imprint of vacuum birefringence, but an indirect effect on the polarization. And this effect is competitive with the depolarizing effect due to the geometry. That is what I tried to explain, because the magnetic field of this star is not uniform. So also, even if the photons are polarized all in the same way, when they arrive to us, if radiation comes from the entire surface, we would see a very low degree of polarization if vacuum birefringence were not present. But if radiation comes from a small spot on the surface, there you can consider the magnetic field as more or less uniform. And so you have not a reduction, an expected reduction of the polarization degree due to the geometry. So you cannot test the power of the vacuum birefringence to maintain the polarization. This is the tricky thing. So in a sense, we could have spotted the first evidence of vacuum birefringence, but we cannot say it with the maximum certainty, because we don't know if the region of emission is large enough to allow a depolarization that can be cancelled by the vacuum birefringence. Hope this explanation is clear, because it's not...
Yes, it's very clear. Thank
Yes.
you very much. Thank you. Yeah, thank you.
You're welcome.
I have a second question is related to the vacuum polarization. I mean, you mentioned the vacuum polarization has never been observed, even the Heisenberg and Euler proposed in 1930s. But I thought the Lamb-Shift and Casimir effect, they got the Nobel Prize. Is it exactly, it proved the vacuum polarization, right?
Oh, yeah, exactly. It's a bit different in reality, because Casimir effect concerns the effect of electric fields on virtual electron-positron pairs, while vacuum polarization is the effect of the strong magnetic field. So in a sense, you're right, of course. Virtual electron-positron pairs are being already detected with the Casimir effect, but not the conclusion that Heisenberg and Euler draw in the paper of 1934, which concerns the effect of the strong magnetic field. And this is investigated, for example, in the experiment PV-LAS, which is, I think, here in Italy, near Pisa, is developed, and they are trying to observe the difference in refraction indices between ordinary and extraordinary mode in the vacuum, highly polarized. So in this sense, it is not being proved up to now.
Okay, but the Lamb-Shift, I think it's the electric field which polarizes the vacuum, right?
Yeah, of course.
Okay.
Yeah, indeed, polarization is, let's say, a wrong term in the sense for the magnetic field. For the electric field, of course, but electric field, the effect is called polarization.
Okay.
Yeah, you are right.
Okay, thank you. But very exciting results and very impressive.
Thank you very much.
Yeah, thank you so much for this interesting discussion. And Keiko, did you have a question?
I do today. Super cool talk. So and also forgive me because I don't know really anything about physics, but or space like that. But I was kind of curious. So like when you guys are looking in space, right, and you're uh seeing these different things like like whether it's like gamma ray bursts or whatever type of light that you're looking for, um, is it possible that the phase of the light could have changed from the source to here? I know like or I think that like sometimes as light can interact with different molecules that like sometimes like have like a chirality, the phase can change. You know what I'm saying? So is it possible that like the reading that you are getting may actually be different because there who knows what that light's encountered and it's like travel to Earth.
Yeah, this is a really interesting question. Thanks. And this allowed me to make more precise one peculiarity of this measurement that I probably didn't stress so much, that this measurement has been done in X-rays. And indeed, X-rays have the property that their interaction with the matter that can encounter the light coming from the source up to us is very particular. So we can see immediately if there are, let's say, interactions with matter that can change the phase of the polarization of the electric field of the light. So in our case, for the X-rays that we measure from magnetars, the trick is exactly that we can say that the phase does not change from the so-called polarization limiting radius, which is the sort of region in which the phase can change, but it is still close to the surface. So from this level up to us, the electric field of photons does not change anymore, despite the fact that there could be some interaction with the interstellar medium. But this is taken into account inside the spectral evolution. But the polarization cannot change in any case because, as I mentioned, it is necessary that a strong magnetic field is present. So even it is possible that it changes if it encounters another neutron star, for example, or for example also a black hole. If it passes near to a black hole, the polarization can change not due to magnetic fields, but due to gravitational fields, because also the gravitational field can affect polarization. And this is important for observation of radiation coming from near black holes. But in this case, we can identify that the radiation has passed near to a black hole. So we can say, okay, we cannot study exactly what these neutrons are emitted, but the effect of other sources in the middle. I hope that I answered to this question. It was very interesting.
Yeah, and do you mind if I ask like one follow-up question?
Mm-hmm.
So, do you then know that as the X-rays escape the source, that the lack of gravity wouldn't change or affect the polarization?
This is another very interesting question because, yeah, in principle, it is possible because, as you probably know, there is the effect of ray bending. So, when the light escapes from a source with a strong gravity, and neutron stars are very compact objects, which are second only to black holes, then the light is bent. The ray is not a straight line, but it is bent. And you can imagine that the polarization plane has to curve as well. So the polarization direction will change. But in the presence of neutron stars, so in the presence of their strongest magnetic fields in the universe, we showed with rigorous calculations that the magnetic field wins on the gravity. And so even if the magnetic field the polarization direction is changed by the gravity, then after a small path of the photon, it is reported to perpendicular or parallel to the magnetic field. Because in any case, for neutron stars, the effect of gravity can occur only very close to the surface, and the magnetic field will last for, let's say, hundreds of stellar radii within 100 stellar radii.
Wow, thank you.
Thank you for the question.
Yeah, thank you so much for those interesting questions, everyone. I don't know how much time you have, but I would have a question for the future, if that's okay with you. But if you need to leave because we've been going over an hour.
No, please. I
Oh,
can answer, of course.
so would it also be possible in the future to maybe observe black holes, and or is someone or are you doing that already? And would there be, would be really interesting to compare, or like a threshold when like enough matter is dense enough to turn into a black hole, and how you know the spectra would look like.
Yeah. So it's a very fascinating problem, that of black hole observations, also for polarization, from the polarization point of view. And indeed, some black hole sources, black hole candidates, have been observed in this first year of operation of the XP satellite. One of the most successful was Cygnus X1, which is a known stellar mass black hole, so a black hole with a mass which is comparable with the mass of a star. And in the case of black holes, radiation that we can collect is, of course, radiation emitted from close to the black hole, because from the black hole directly cannot arrive any light. And so we can study the effects of the presence of the black hole for this particular light. The problem is that the black holes, at least for what we know, the theory, the Einstein's theory is very well verified, there are no effects like, for example, for neutron stars, the magnetic field that can strongly polarize initially the radiation. So there is still an effect that can polarize, because if we have non-polarized radiation at the start, we cannot study the polarization at the observer, of course. So we need that the source collaborates in a sense, and it polarizes light near to the emission. And for black holes, this effect is not the magnetic field, but it is the scattering of light, for example, in an accretion disk around a black hole, or in other structures around the black hole that are called coronae around the black hole. And these can be studied. So there are expectations of the polarization. I also performed a study about what could be the polarization of this kind of sources. There are many hypotheses. We don't know exactly what is the right one. In the case of Cygnus X1, it was the polarization measurement was sufficient to see that the black hole probably is inclined with respect to us with a certain angle. So polarization measurement have been performed, and they are feasible in principle. The only problem is to find the right black hole that we collaborates with us and as a sort of initial polarization, which is the important thing to be observed.
Yeah, thank you. And is there a tendency in a specific place where you're looking at that has a lot of magnetars that have similar characteristics, or are they scattered all over?
So for the moment, magnetars have been observed. The magnetars that have been observed are 25, I think, if I remember well, and they are more or less scattered on the disk of the Milky Way. So they are, as I mentioned, galactic sources. If you go at slide 22, you see that the second one is exactly on the disk of the Milky Way. So many others are inside this region. Curiously, the first one, which is also the brightest one among magnetars, is not in the disk, because it is in the northern sky, so it is scattered with respect to the disk. But the major part of the magnetars are on the disk. The problem with magnetars to be observed in polarized light is that they are faint sources with respect to other sources, like, for example, those of black hole candidates. The two that we have observed in this first year of operation of XP are the brightest ones. For you is the brightest in general, and 1RXS is the second one, the second brightest. We are trying to perform, so we proposed to the collaboration a third magnetar, which is called 1806, if I remember well. And this is an interesting source because, yes, it's fainter, but in 2004, it produced the strongest the strongest X-ray explosion ever detected in the last decades. In 2004, it was the last one observed from a neutron star. And it is a very active magnetar, so it could be very interesting to study radiation coming from this particular source. The only problem is that it is faint, and polarimetry is a photon-hungry technique, so it does need of a large number of photons to say something. Probably future missions, and there are, for example, there is a Chinese mission that should be launched in the future, 2027, I think, that has a sensitivity greater than XP. But for the moment, we have to limit our research to bright sources. And so let's hope that the next source is sufficiently bright to be observed in a certain sense.
And does the activity or also the pulsing have to do with in what stage of the magnetars they are? Like, is there a theory about if they are earlier stage, later stage, if that activity changes?
So there are different hypotheses about the stages of life of magnetars. For example, among isolated neutron stars, there is a class which is called X-ray dim isolated neutron stars that, as the name suggests, they are dim sources. And these are believed to be old magnetars. So magnetars that have, in a certain sense, no more power from their magnetic field, and so they cannot exhibit anymore the strong activity of the active magnetars. So in a sense, the they still have a stronger magnetic field than for pulsars. So there is this line of evolution towards a less activity. So the key, in a sense, is if you see the power law tail, as I mentioned, we have in a stage of activity. If you don't see the power law tail for many time and you don't see explosions or glitches, so irregularities in the motion of rotation, and so on and so forth, you are going towards a stage of let's say maturity of the neutron star that probably will settle as a whole the neutron star, as an X-ray dim isolated neutron star.
And sorry to keep asking, but do you think the crust will change, that there will be less crust or no crust and maybe no atmosphere then anymore also?
So
Or yeah.
for the atmosphere, I think that it can change, of course. For example, the mechanism that I illustrated, in which literally the atmosphere can rain on the surface of the neutron star, which is called magnetic condensation. So it is possible that if a neutron star show an atmosphere in a moment, they can show the solid surface in another moment because of particular phenomena on the surface. It's less. It should be strange if the crust change too much, for two reasons. Let's say the first one is of fundamental physics, because the neutron stars are made by the core of the original stars, so the matter is let's say ordinary matter on the surface, and it should not change in time, because essentially protons does not decay. Neutrons can decay, but with the density of neutron stars, also neutrons, let's say the decayment of neutrons is balanced by the formation of neutrons. And the other reason is indeed the density of the neutron stars. So also when star quakes can occur, that someone imagined that the star quake is like an earthquake with fracture of the crust. This is not really true, because in the presence of such strong densities, it is impossible to crack the crust. It can deformate like a sort of mayonnaise, but it cannot crack. So there are differences, but it is not excluded that we can study it with the polarization. We have only to put in order all the information from our theoretical models.
Yeah, interesting. And one last question: do they differ, or can you know if they differ a lot between the different type of elements they are made up of, or are they very similar?
This is a really interesting question, because in our paper, we considered an iron condensate. So the solid surface is made by iron, let's say, which means very EV elements with an atomic number of 26 and a much greater number of neutrons, because they are on a neutron star. But there are many models according to which there could be a surface of light elements like helium or carbon. They cannot be heavier than iron, because iron is the limit nucleus that can be created in nucleosynthesis inside stars. So there could be some strange matter like neutron-rich nuclei, but not let's say, with an atomic number greater than the iron. But there are, yes, there are different expectation for the polarization and also for the spectrum of surfaces with different compositions. So iron, carbon, helium, and so on and so forth.
Well, very interesting. And no lithium?
Oh, lithium, I think it could be difficult in the sense that for the abundance of lithium inside stars, because inside stars you have different stages of nucleosynthesis. The first one is the hydrogen into helium, and the second one is helium into carbon. So lithium is in the middle, and it is probably unfavored to be created and to be so much abundant in the neutron star surface to be seen.
Well, thank you so much. This is so interesting. I'm really, I really appreciate the time you took to present this really exciting, groundbreaking results and to answer all of our questions. So thank you so much. And
It was my great pleasure.
yeah, I hope.
Karina, can I
Yeah,
squeeze
go
in a
ahead.
last question?
Yeah, please.
Oh yeah, so Roberto, thank you. I second all the speakers. That this is really fantastic, and great groundbreaking results. So yeah, after reading more attentively, I think I got my own question answered. So for now, I got so the low energy versus the high energy. Is the high energy that the QED effects took effect, right? Just
Yeah, exactly. Yeah.
Okay. So then then essentially the scattered ones that the from the atmosphere will give you the 1/3 mix polarization, right?
It's not from the atmosphere, but from the magnetosphere. The atmosphere
Yeah,
is
magnet.
exactly.
Yeah. So, I guess I'm asking specifically the slides number. Let me see, it's 20, right? So the blue arrow that you're basically indicating that it's the with and without scattering. Am I correct?
Exactly. On the left, you have without scattering, so there are the different curves correspond to different line of sights of the neutron star. Then the blue arrow indicates what happens when you add scattering to this receipt.
I got you. So then, so by this evidence, you also show that during different phases, in two observations, you don't see this repeating itself. At one time, you do have strong evidence that you see the two perpendicular polarization, and then in the 27 slides 27 you show. So what is the what type of activity on the star? What kind of is so there's some sort of as I heard. I'm just trying to confirm that is the it's like some sort of before maturity is very active, so that this
I
scattering
understood the
is
question, and yeah, perfect. Probably it's a confusion that I created when I answered to the previous question. Probably you mean you refer to this second magnetar in which I say that there is no power law because probably so in the previous observations we saw a power law. Now we didn't see a power law, and this does not mean that necessarily the star is becoming old, but there could be different phases along a neutron star. If you go to slide 8, this is typical by the twisted magnetosphere scenario proposed by Thomson et al. In 2002. So in a sense, the magnetic field inside the star, which has this, let's say, transversal component, is sufficiently strong to deform the crust. The crust is deformed, and the field lines, as you see in slide 8, rotates and gives you the twist. The twist extracts the particles and makes the magnetosphere, and so the power law tail. But then the twist can return to zero because the rigidity, in a sense, like a sort of spring, no, is released. So until the next great release of energy, we will not see another power law. Maybe in few years, the source will show a glitch, which means an irregularity on the rotational motion. And this means that the crust have been cracked, let's say cracked, in a location. So if we could observe the source in that moment, probably we will see again the power law.
Yeah, that's fascinating, very interesting. So, what is the periodicity that, according to this Thomson model, of this
Okay,
questioning?
the periodicity for the short, there are different kind of explosions. There are short bursts and intermediate slash giant flares. Short bursts have a periodicity which is many in 1 year. So a number of events in 1 year. Intermediate flares is much rare, in the sense that you can have some events like, for example, an earthquake in a particular location of the Earth. And finally, the giant flares, we only saw 3 events starting from 1979. The first magnetar was observed for a giant flare. Then we observed another in 1999, and another one in 2004, that is what I mentioned in one of the answers. So only 3 giant flares, some but rare intermediate flares, and much short burst.
Wow, so this actually make it feasible for you to actually plan your observation window to verify the part.
The only problem is that the short bursts are really short, so the duration could be 0.1 second. And the problem is that pointing the source, the source with the instrument, you can, for the major part of the observation, you cannot match the short burst. The ideal thing should be to locate an intermediate or a giant flare, which can last for thousands of seconds, and so you have the time of pointing the satellite to the source. The problem is indeed that we have no events. So the last one was in 2004. Let's wait for another one.
That's so cool. Yeah, thank you, Roberto. This is fascinating.
Well, yeah, thank you so much. Again, this is really fantastic, and I'm so glad you made the time to come here and share this with us. And yeah, we wish you all the best and all the luck and a lot of funding.
Thank you. And also to your and to your channel, which is very interesting.
Oh, thank you. I really appreciate hearing that. Thank you so much. And thank you everyone for coming, asking questions. And yeah, it was a really wonderful discussion. I really appreciated it. And enjoy the rest of your day. I know for Frank it's already late or morning, wherever you are. And I hope I hear you all back soon. And the next discussion will be with Dr. Stöger, talking about aging due to unbalanced gene expression. So, yeah, it will be a different type of discussion, but I think it will be interesting. And yeah, thank you, Roberto. Good luck for everything, and congratulations again. I'll close
Thank you. Bye bye.
Thank you. Bye. And 3, 2,
Thanks.
1. Bye, everyone.